Hi, so today I'll go and show you some example about using flow simulations CFD with SolidWorks. So this tutorial will be working with the following topic, and we try to address how can we set up the model. So the first example I would do, what we call it is internal flow. But before that, it's very important for us to save the file on the folder. So I will create a folder in my desktop. I'll call that folder like CFD example 1. And then I will call this one pipe. So we do the pipe CFD question. I like to use plain white. And first we need to extract the CFD or we need to activate the flow simulation. So if you haven't done that, you come to this options, click on the arrow, add-ins, and from add-ins, you click on SolidWorks flow simulation. This is a student version just to show you how it works, okay? When you click that, it will take time and then refresh, and then you get that flow simulations ready for you. So first I will choose the front plan, and I will sketch a pipe. Let's say the diameter for that pipe is 25. Make sure I'm working in millimeters in that system, millimeter gram seconds. And then I will sketch another circle, internal one, with the dimension, let's say, is 22. Then I'll extrude that because there are two circles. Extrude will take the thickness to create that pipe for me. I'll give a dimension for that pipe. It's like, let's say 500 millimeters as a distance. I could choose to make it mid-plane, for example, which is a good option because we want to keep everything in the centroid, and we can create that to get more information and data. Make sure every time you work with CFD simulations to save, because sometimes if the software crashes, you always, we can go back to where you have stopped. All right, so very simple pipe. I want to check how is the flow simulation. We go through the pipe. Possibly I want to see the difference between laminar and turbulent flow with respect to velocity profile. All right, so go to flow simulation. I have the following option. I click on the wizard. I will call this one pipe 1 as the first design. You can keep the configuration as current. And next, here you have the SI units. This is very important if you want to work in different unit systems, but also you could change as well the units for the SI unit system. So for example, very common, some people, they don't want to work with kelvins, they want to work with degrees Celsius. You can come here and change that to whatever temperature. For me, I'm not bothered at this stage because I'm just doing a normal adiabatic system. Next is the fluid flow. Conduction, I don't have it. Time independence is when you're running some type of time analysis, transit analysis. I'm not doing it at this stage. Gravity, I want to take gravity into consideration. You see the Y is going upwards. Then if I want to have the gravity at the moment is in the wrong direction, it's showing me in the negative Z direction. But I want to make it in negative minus 9.81 in the Y direction, and this one I'll make it 0, and therefore you can see is matching the right gravity based on what I assume it. All right, so that is the gravity. Rotation, we don't have any issues. Free surface, not really. If it's external flow, we're trying to find the airflow around an orifice or around the tube. Not really. I'm trying to achieve here an internal flow. And the internal flow, the software will ask you to create a lid to make it a watertight geometry. Keep the CAD information here, like don't change anything. Mesh, like this is later, we go for advanced. Exclude cavitation without conditions. You can untick that or tick it. Let's keep it. And then next, will not bother me. We need to select the fluid to bring the material properties to calculate Reynolds number. By default, you have water selected. Two methods. Either you click and add and will be added here, or you double click on the water and then you find the water liquid is added here. You have the option to choose flow type laminar, turbulent, or laminar turbulent. I would select laminar and turbulent because my problem could change. Cavitation, I'm not including any heat or anything or long vibrations to code for me the kind of like heat generated through the friction through the pipe or anything like that. So no. As I say, it's an adiabatic wall. Roughness, we assume this is a new pipe, clean one. And then the initial boundary conditions, we leave them like they are. Pressure is the atmospheric pressure, and temperature is room temperature. Initial velocities are zeros for the X, Y, and Z directions. Turbulence, intensity, and length, I will leave at this stage 2% the intensity, and turbulence length, keep them like that. When you click finish, you'll see a window pops up here with all the setup for the flow simulation. Fluid volume recognition, it say to me, has failed because the model currently is not watertight and internal task must have been sealed to internet. So don't panic from that. Say, yes, I want to watertight that, and it will ask you to select the faces. So you select that surface, and then you get the first lid. We call it lid, and the second one to create the lid too. And then when you click OK, create lids, you see now we created the lids and update the computational domain, and now we are okay with that. Since I cannot see through, I could make that a bit hidden. So I can see now inside the lid. Okay, so the cubic shape of that rectangular shape is representing for me the computational domain. It's trying to, as much as can, to cover the entire cylindrical shape or cylindrical volume for the water. You have the following things: information, input data. Right click, you can new parametric study, column project. If you want to copy it, check out the information, the setup we done. Input data here. If you want to go back to the general setting, you say, oops, I forgot to add something. You click on that, you can update the general settings, such as you can include time independence, you can change whatever things we have done. So always, if you made a mistake or you want to update the project, you could come to input and general setting. Units as well, competition control, global mesh, and all the remaining information. Now, for CFD analysis, you have always inlet and outlet boundary conditions. You may have multiple inlets, multiple outlets, or one inlet, multiple outlets, or many inlets, one outlets, but you should have always inlet and outlets. So we try to create those boundary conditions go through it. But also I need to talk about the computational domain. If it's showing you the conditions, usually the software pick it up by itself. But you can adjust that in a case you want to increase that computational domain by just increasing these values or expanding these arrows. The other option as well is if you have fluid subdomain, you can add it if you want to create a mix between air and fluid, whatever things you could have in your applications. Boundary conditions, insert. I'm inserting at the first is inlet velocity. In that direction, my velocity is 2 meters per second. Which based on the fluid, that would cause me a turbulent flow, and we check that. Since I've selected that, the face, when I click OK, you'll see the direction of the arrows. And very careful, you see it's covering exactly inside that box, which I'm showing to you. If that box moved a bit slower, will give me an error, and you can fix it easily by adjusting the computational domain. Okay. That's number one, first boundary condition. The second boundary condition, insert boundary condition. You select that face, the other one. Here we always select environmental pressure because it's open to the atmosphere, and we can keep it P gauge is 0, but you have the atmospheric, so the absolute value would be atmospheric pressure. Room temperature about 20 degrees. Celsius, and the remaining if it's you want to add other properties. Something I could also include with this is the goals. I could either select goals from this option, or I could also, when I edit my velocity, I could come to the goals section and select, for example, if I extend this further, I want to know the mass flow rate average value, the total pressure average value, and that way will give me some goals selected from there. So two ways, you can either select these goals from the boundary conditions, or you can come here, goals, and you say insert surface goals. Say which surface. I have two options, either to select these surfaces easier. Other option, you could select the inlet velocity, and by automatically will select that surface for you. And you call it, I want to see the average static pressure. Enter. And then the other goal in surface goal, and come here, I could select from that, but I'm showing you the other option. You go and select from the boundary condition. It selects easy as well. I will select the average static pressure at that point. Another things we could do is to select the goal equation, insert equation goal. So you have static pressure 3 minus static pressure 4. You can choose from this operation, and that we call it pressure difference. Happy with that equation, you can tick OK here. Global mesh in this kind of applications, it's very simple. You can adjust, it's always set to the 3, but you can adjust it to 5. It depends on your computer. This type of problems, it doesn't need 5, but I'm just doing it to show you how can I adjust that. Now we finished the setup of the geometry and everything. I could now run simulation. You have multiple ways. It's funny. SolidWorks give you multiple options to run. One, you can come here and say run. One, you can come here and say run. One, you can come here and say run. Other option is you go to tools, and from tools, you can find or simulations. No, that's for FEA. Tools, flow simulation, and solve and run. So many different ways you can run this. Choose anyone works for you and run the project. When you run, you find a window will appear to you, this one, to say about running this computer, yes, and then you get another things to run the software for you. This one to show you the setup for the velocity. I took some contours in advance before, so my computer always select this. This is showing you the stabilization to reach the convergence for the parameters I'm monitoring. Good things is no warnings. It's telling my computer, it's telling number of cores I'm using, for example. Finish, very easy, no problems. As soon as finish, you find the file called 1.fld, fluid extension. It's loaded, so now I have the results. Let's explore the results. Let's see this front view and cut, insert. In that cut, you can select front plane. Doesn't give me much information. I can change it to top plane. And I want to see the vectors instead of pressure, maybe velocity. And then click OK, and then will load up for me the velocity. You can see nicely the contours generated from this velocity. All right, don't want that contour. Hide, cut plot again, insert. I want the same one, but instead of this would be pressure and maybe showing streamline. Or maybe just pressure vector. Enter. Oh, I didn't select the right plane. I selected this one. So you say, what's happened? It selected this plane, which is that pressure on that plane. If I want to change it, very simple, edit definition, comes back to me, hey, you're not happy with this one. Yes, I want the top plane, and then click, and now you change it to that is the top plane for the results for the pressure. But you can explore that as well. Another option as well, people like to do, not in the cut, so hide this one. You can go to flow trajectory, insert. I prefer to insert to start flow trajectory from the boundary condition from the inlet velocity, which is mean again, I'm selecting this phase, but I'm going to more about my inlet velocity to ensure you're going through it. You can change it's already set up for me lines. I can choose lines with arrows, and then that will demonstrate for me pressure. I change it to velocity, and then run, and then you can see this is how it nicely. If you go and click again flow trajectory and play, would generate for you a nice motion how the things would go through it. All right. Still remember, I hidden the pipe, so it's still showing things going through it, but I hide the pipe to make sure like you can see through the simulations. Okay, something else we could do with this simulation. Remember the goals we did pick up here. We can actually display them. So double click on goals, insert goals. All the goals, we select them, show, it's showing me the properties. If I want to export them to Excel, just click on export to Excel and they will generate for you an Excel sheet. So that's another things to show your goals. Show, you can present them here as well. If you want to go plots, for example, if they have something you're interested in. Otherwise, hide if you don't want to show them. XY plane. I don't have an XY plane, but I want to sketch something. So I go back to my sketch. This is my front or top. And actually, I will select the front. No, top. Top is good, or right plane. Right plane is good. Let's make it to face me, because that is the direction of velocity. And then sketch. I could sketch a line. So line coming here, and make sure it's covering the boundary computational domain, and exit that line, and then I select another line. Okay, right plane, another line here, exit. And also I could select a line between them. If I want, no, I need to exit the line because I don't want, I'm creating separate lines. Top plane, make it to face me. And then based on these 2 points, I could select a line on top of them. And now you can see how I generated the lines. These lines, if you can look into them, there is no relationship between them. Name them line 1. It's just random lines. I select them, but I want to see the velocity profile along these lines. Line 2, and the last one, line 3. Okay, so I want to see how is the velocity going through this pipe, the one I'm hitting here, and go through it. So go back to the simulation, XY plot, right click, insert, select the first line and line 2. 2 options. I can either select from the figure itself, or I can come here from that tree and then select line 1 and line 2, similar as because selected. I want to see first the pressure. I want to see the velocity. I want to see the velocity in X, Y, X, and Z as well. Show. Here is showing you the velocities. The most important one is the velocity average one. And it's showing you, for example, the velocity in Z direction is more important. So I remove the X and Y and keep the remaining. And I click show again. So this is showing me the velocity. By the way, I could export that to Excel file. Showing the pressure along the lines, this line and this line. And it's also showing me the average velocity, and it's showing me the velocity in the Z direction. All right. Happy with that. You could also investigate the pressure along the other line 3. XY plot, insert, select line 3, and then I want to see the pressure along that line, show, and showing me how the pressure is changing. Now, because it's a straight pipe, I didn't make any changes to it. It's very easy to see that velocity. Now, if we go back to velocity 1, I can say show. It shows me only the first one, but I could really just say, okay, insert line 1 and 2, show me velocity Z, show, close, and then hide that one. And I see, show, that is showing me how it's a turbulent flow based on the velocity profile we're getting from that distance to that distance, which is less than 0.025. The entire outside diameter 0.25, but it's less than that. So it's technically, it's showing me that the flow is actually, it's turbulent. Now, let's reduce the velocity and try to investigate that with laminar, because this is a turbulent flow. You can check that with the properties of the fluid at room temperature, and as well check that with the diameter, internal diameter. So if I want to do this simulation, first save. Secondly, right click on pipe, clone. Clone is mean we'll repeat everything, but you could call that one O2, second simulation. This one, you don't need to change the geometry of the pipe, you just change the physical, the properties you set up. So for example, I could come here and say inlet velocity, instead of 2 meters per second, 0.01 meters per second, small velocity. And then, okay, I will not change anything else. I'll just say run this simulation. We'll go through the process itself again. It will run for me again. The velocity is showing me now the maximum, how it looks like. That is actually is trying to run the solution for laminar flow until stabilization reaches for the goals, pressure difference and everything. Now I'll show you, because I kept these velocities. This is the situation when you have what we call it, you can see in the result when you have turbulent flow or when you have laminar flow. Let's check that with the results. First of all, if you check here, it's became 2 FLD. For first result, pipe 1, O1 was 1 FLD, now it's 2 FLD. Now, if I do these plots, will not show anything for me because nothing is being selected. So that's why I say always do a new plots or edit the plots. Insert line 1, line 2, and velocity in the Z direction. Show, you can see nicely, I'll bring that, plot 4, show, you can see nicely how now it's a laminar flow, because in the laminar flow, you will get the maximum velocity clearly outstanding there from 0, the wall, going to the maximum, and usually we use the average velocity to calculate that. So here is technically the maximum velocity, which we can get that value for it calculated as well. All right, so that is confirms for me the model is working, predicting for me if it's laminar or turbulent flow for this type of simulation. I also could show, play the flow trajectory for it. It's slightly different from what we've done in the previous simulation, because now the flow is laminar. It's not like turbulent, how it used to be going through it. I hope that video is enough to show you everything about a simple application for internal flow analysis. Thank you.